Okay, we'll start with the class. So, good evening, everyone. So, this is the final class for the NPTEL online certification course on water and wastewater treatment. So, this is actually an extra class for the problem solving and doubt clarification. And this course was taken by Professor Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Saha, and I am a PMRS scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. Okay, so just a minute. Yeah. So since this is the final class, I have collected some questions related to all the topics that we have discussed, or mostly those topics which we have not discussed in detail. Okay, so all these questions are basically numerical type questions, and it may seem lengthy subjective type, but it can be broken down into several MCQs, and then it can be asked in the exams. So I have collated questions like these related to various topics of water and wastewater treatment, which we have seen in all these 12 weeks of lectures. Okay, so let's get on with it and start with the first question. So yeah, it may look like a very big problem, but all these subparts like A, B, C, D up to F can be asked individually as an MCQ. Okay, so that's why in one synchron problem I tried to address all the various aspects related to a particular problem. Okay, so the first question says that a chemical supplier reports the concentration of stock alum chemical as 8.37% as Al2O3 with a specific gravity of 1.32. Okay, so a stock alum chemical has been given whose percentage as Al2O3 is has been reported, that is 8.37%, and the specific gravity is also given. So for this chemical you have to calculate what would be the what would be the molarity of Al3 plus ions, and then the alum concentration if reported as gram per liter of Al2SO4 thrice dot 14H2O. Okay, so generally we the like report alum in terms of Al2SO4 thrice dot 14H2O. So what will be the alum concentration? And then it says that also for a 30 milligram per liter of alum dose that is applied to a treatment plant with a capacity of 43,200 meter cube per day or 0.5 meter cube per second, calculate the chemical feed rate in liters per minute, then the alkalinity consumed, okay, in milligram per liter as CaCO3. Then what is the amount of precipitate that is produced in milligram per liter and as well as kg per day, and also at last the amount of NaOH that would need to be added to counteract the consumption of alkalinity by alum. Okay, so all aspects of alum addition to the wastewater treatment plant has been covered in this one single problem. Okay, how to report the concentration. So starting from how to report the concentration to what will be the alkalinity consumed, how much precipitate will be formed, how much NaOH has to be added. So everything we can solve, and it's kind of a design. Okay, if you are going to put alum, okay, so what are the aspects that if you have to take into consideration, right? So I'll give you some time to go through the problem again, and then I will give you the solution. Maybe you can try it out, the first few parts, and then we'll see how to solve it fully. So all these subparts can be asked individually as an MCQ problem. Like they will give you the concentration and may ask what will be the alkalinity consumed. Okay, so there you have to know what will be the equation of alum, what is the reaction. So with the help of that reaction, you will be able to find what is the alkalinity consumed and or what is the precipitate that has been formed. Right? So let's see the solution. So this is the first question. A part. So it has been given that the density of the stock solution is around 1.32 kg per liter. So when density is given, so it's easier to calculate the concentration. So the concentration of stock solution will be equal to, since it's a 8.37 percentage, so we will take 8.37 percentage divided by 100 into the density. So 1.32 kg per liter, and I will change kg to grams. So 10 to the minus 3 gram per kg. Okay. So we can get it as 110.5 gram per liter, and this percentage was given in terms of Al2O3, so it will be 110.5 gram per liter Al2O3. Okay, so directly from the concentration, directly from the density, we can get the concentration, right? So amount that is present in 100, so 8.37% we can find out. Now, the actual question was to find out the molarity. Okay, so molarity of the Al3 plus ion. So once we know the concentration of the stock solution, we can then find out the molarity. So Al3 plus molarity, we can find it out. So the concentration is 110.5 gram per liter of Al2O3. Okay, and per mole of Al2O3, what is the mass? If you find out the molar mass, it will be 102 grams of Al2O3. Okay, so per mole there is 102 grams, and 1 mole is having 2 moles of Al3 plus. Okay, so per mole of Al2O3 we have 2 moles of Al3 plus, because we want to find out the molarity of Al3 plus. So that's why this 2 will come into the picture. Okay, so if you solve this, you will get it as 2.17 molar, right? So that's how you have to solve it. So this was the first part, and in the second part it is asking what is the concentration of stock solution in terms of alum. So this we found out in terms of Al2O3 in the previous thing. We will find out in terms of Al2O3. Now we have to find out in terms of alum. So it's nothing but C stock in terms of alum will be nothing but 110.5 gram per liter of Al2O3, and we have to divide it by the molar mass of Al2O3, that is 102 gram per mole of Al2O3, and then multiply with the molar mass of Al2SO4 thrice dot 14H2O. So that is 594 grams of per mole of alum. Okay, so this alum is nothing but Al2SO4 thrice dot 14H2O. Okay, so if you just simply solve it, you can get 643.5 gram per liter of alum. Okay, so these are the first two basic parts: how to calculate the molarity of Al3 plus ions, and then the stock solution concentration in terms of alum. So you just have to play with the molar mass and the molecular. That's all. Molar mass you have to know for all the various species that you are trying to find out. Okay. Let's go to the third part now. So in third part, what was the third part? Let's see again. So the third part says that what is the chemical feed rate in liters per minute? Okay, if a 30 milligram per liter of alum dose is being applied, so what will be the chemical feed rate? So nothing, we have to just use the mass balance. So by mass balance, we can say, so we can say the C concentration of stock solution into the discharge of feed will be the concentration of the process, whatever is going on, into the discharge of process. Okay, into the discharge of process. So in that way, we can just find out the feed rate. So feed rate is nothing but the discharge. So concentration of process will be 30 milligram per liter, and Q of process will be 43,200 meter cube per day. Okay, yeah, for meter cube per day. And just I will convert liters to meter cube. So 10 to the 3 liter per meter cube. And what is the C stock? So C stock also we found out 643.5 gram per liter, and I will change milligram to gram, and I will change minutes to days. Okay, otherwise it would have been a very big number. So the final answer will be in liter per minute, because that's what they want, will be in liter per minute. So 4.10 liters per minute. Okay, so that this is the overall mass balance. And the next part they are asking how much of alkalinity will be consumed. So for alkalinity consumption, we just need to know one single equation. So the equation is Al2SO4 thrice dot 14H2O will give you 2AlOH thrice. So this is the precipitate, plus 6H plus 3SO4 2 minus plus 8H2. So this is the overall equation. So from here we can find out the alkalinity consumed. Okay, we can find out the alkalinity consumed, and also we can find out what is the precipitate form. So my alkalinity directly can be found out. So how much alum was added? Or it was 30 milligram per liter of alum. Okay, and 1 millimole of alum is equal to around 594 milligram of alum. So just dividing by the molar mass into, now for alkalinity consumption we have to see how much of sulfate or acid neutralizing capacity is there. So it is 3 millimole of sulfate per millimole of alum. Okay, so 3 is the coefficient, so into 3. Then how many milli equivalents, because the power is there, so 2 milli equivalents of sulfate per millimole of sulfate. Okay, so since 2 minus is there, so 2 milli equivalents of, because everything we are trying to convert in terms of milligram per liter as CaCO3. So whenever we are finding, as we have solved many problems before, we want to find out what is the milli equivalent. So that's why that 2 factor is coming into the picture. Then again multiplied 1 milli equivalent of alkalinity per milli equivalent of SO4 2 minus. Okay, so now we are slowly changing into alkalinity terms, and then 50 milligram of CaCO3 is equal to 1 milli equivalent of alkalinity. Okay, so this may look very big, so nothing but you have to multiply the concentration of alum, divide by what is the molecular mass, okay, into how many parts of sulfate has been formed. So 3 parts, into what is the carrying capacity into 2, and then 1 milliequivalent is equal to 1 millikilo of sulfate, that is nothing but into 1 into the milligram as CaCO3, so 50. Okay, so this is the basic thing. I'll just rub it off. Okay, so if you just solve this, you will get it as 15 milligram per liter as CaCO3. Okay, so it all depends on this particular equation. So if you know this equation, the top equation, you can solve whatever is asked. All right. Uh, Now let's move forward to the next part. So the next part is asking for the how much precipitate will be formed. So so precipitate we can see per mole of one alum, we are getting 2 moles of precipitate. Okay, 2 moles of precipitate, that is ALOH size. So again, precipitate formed, that is ALOH thrice. Okay, so 30 milligram per liter of alum. Again the same thing, 1 millimole of alum is having 594 milligram of alum. How many precipitates were forming per mole of alum? It is 2 millimole of AlOH thrice per millimole of alum into what is the weight of alum. So weight of the precipitate. So 78 milligram of Al2O thrice divided by millimole of AlOH thrice. So simple thing. So it will be 7.88 milligram per liter. Okay, milligram per liter of AlOH thrice. Okay, so this much amount of, so here this 2 is the coefficient that we want to focus on, because per mole of alum we are getting 2 moles of precipitate. Okay, so that's why that 2 is coming. Rest are just molecular weights and all. So this was in milligram per liter. So in kg per day, if I want to find it in kg per day, it will be 7.88 milligram per liter into 43,200, that is the discharge meter cube per day. I'll just change meter cube into liters and the milligram to kg. Okay, so it will get us 340 kg. Okay, so just make a note of it. Okay, and the final question was like asked was like how much of NaOH has to be added. So for this another equation we should know. So this is nothing but Al2SO4 thrice dot 14H2O will now have to act with NaOH. So the equation is 6 NaOH will give me 2 AlOH thrice plus 3 Na2SO4 plus 14H2O. So here the major part is how much NaOH, that is 6 NaOH. Okay, so coefficient will be 6. So how much NaOH required? NaOH required will be equal to 30 milligram per liter of alum, 1 millimole of alum by 594 milligram of alum, 6 millimole of NaOH, because that's where the equation is coming, per millimole of alum into 40 milligram of NaOH, because that is the molecular weight, divided by millimole of NaOH. So this will be equal to around 12.1 milligram per liter NaOH. Okay, so that's it. So this is how you have to solve it, right? Just a minute. Okay, so let's solve the next question now. So it's basically a graphical question, but it will give you an idea of how the Freundlich and the Langmuir isotherms that we have seen in adsorption, how we have to find out the various parameters related to them. Okay, we have seen the equations of Freundlich and Langmuir, but we don't know how to calculate those parameters. Okay, so this question will give you an idea on how to experimentally get the parameter values of the Langmuir and the Freundlich isotherm. Okay, so it says that for experimental isotherm data given below, determine the Freundlich and Langmuir isotherm parameters. Apply linear regression to determine the isotherm parameters. Experiment data are that the carbon type is F400, carbon size 200 into 400. These things are immaterial. We don't require all this information to solve this problem. It's just given the background information. Chemical is trichloroethane. The temperature is 13 degrees Celsius. pH is 7.5 to 8. And equilibrium time is 31 days. So all these are background data. We don't need them to solve the problem. But here you can see that samples are being collected, and the liquid phase concentration as well as the concentration on the absorbent phase. Okay, so both the things are given in the question. So from here you have to find out the different parameters for the Langmuir and the Freundlich isotherm. So the liquid concentration is nothing but the concentration in the solution, that is the Ca. Okay, concentration and solution, and the absorbent phase concentration is nothing but the Qa. Okay, so these terms we have seen in various problems in the previous sessions. So I'll just tell you how to solve the problem. So first is the serial number. I told you that the first thing given is Ca, okay, the concentration in the bulk, and the Qa, that is the concentration on the absorbent. So I'll just write down the values. Because these are the values given. So for solving this problem, we need to find out some more terms based on these information given. So we will calculate. So I'll just tell you what are those parameters. So first is we have to find out Ca by Qa. So just divide these two columns. So if you do this, we will get it as Ca by Qa. Okay, so this is the first parameter we need. Then the next thing that we need is log to the base 10 of Ca. Okay, so this is required for the Langmuir isotherm, and the next two things are required for the Freundlich isotherm. Okay, so we need log, Ca, and we need log Qa. So I'll just write down the values. So this will be much easier to do in Excel. Okay, so by Excel in by one command, you will get the answer. So I solved this in Excel, but now I'm giving you this the solution. So that later if you do it in Excel, you can cross check. Okay, so these are the values that we get. Okay, so first we will see the Langmuir isotherm. Okay, so the Langmuir isotherm, the equation is nothing but Ca by Qa is equal to Ca by Qm plus 1 by Ba Qm. Okay, 1 minute. Right, so this is the basic equation of Langmuir isotherm. So whatever data is there, if you can fit within this equation, then it's a Langmuir isotherm. Okay, so for here it is nothing but as same as y equal to mx plus c. Okay, here my x is nothing but Ca, y is nothing but Ca by Qa, my m is nothing but 1 by Qm, and my c is nothing but 1 by BaQm. Okay, so if you get x, y, m and c, we will able to find all the parameters. Okay, so seeing this equation, we have to plot a graph between Ca in the x-axis and Ca by Qa in the y-axis. Okay, if you solve it, you will get something like this, some dots like this. Okay, with all these informations, maybe more than 6 or 7. So if you plot between Ca by Qa and Ca, okay, you will get a plot something like this. Okay, then in Excel there is a function through which we can make a trend line. Okay, so it will give a maybe a trend line, like what is the equation that these points are following. So this is nothing but a trend line. Okay, so when you get this equation of the trend line, the equation you are going to get for these parameters will be equal to y is equal to 0.001 to x to 127x plus 0.0033. So this is the trend line equation that you will get, linear trend line. Okay, so by linear regression, you will get the equation of the trend line as this. So here again, you can now, as I told you, this is nothing but m, this is nothing but c. So this resembles as y is equal to mx plus c. Okay, so from here we can write it as m is equal to 0.00127, and I told you m is nothing but 1 by qm. So my qm, that is the first parameter, will be 1 by 0.00127. So 7 at 7.4 per gram. Now, if I want to change into mu gram per gram, I will just multiply with the uh, molecular weight of the contaminant. Okay, so now I will just simply do. So we'll get it as, okay, so this is for TCE, the contaminant that is given. Okay, and then we know C is nothing but, and that is equal to, so we know what is the value of QM. So BA we can find out another parameter for languid or you can write it as 2.9. Okay, so this is how you have to do it. Okay, just go through it once again. So this is the basic equation. Okay, here are all the parameters. This is the fitting of the curve. Okay, and then the values. So these are the, okay, so that's how you have to solve the first part, that is for the friendly isotherm. As for the Langmuir isotherm, now we will solve how to get the parameters of the friendly isotherm. So here again for the friendly isotherm. So as we have calculated uh, log QA and log CA, so we will make use of this and we will first plot a graph between on x-axis log CA, y-axis log QA. Okay, so again we will get some points like this maybe. Okay, so we will make a trend line out of it. We will make a trend line out of it and we will find out the equation. So the equation of the trend line will be nothing but y is equal to 0.4327x plus 2.2831. Okay, very easily we can get it. And what is the general equation? General equation is log QE is equal to log K plus 1 by N log C. So this actually comes from the equation Q is equal to kc to the power 1 by n. So if you just take the log of this whole equation, you will get this. Okay, so this is also same as y is equal to mx plus c. So m, or I shall say the slope, will be equal to 1 by n is equal to 0.43. So this is the one. Okay, and log k, that is the intercept, is nothing but 2.28. This is this one. Okay, so easily we can get it. So now once we got log k, so the capital K will be nothing but 90 mmol per gram. So just you have to take care of the units to the power 0.43. So I can just change to 90 mmol per gram into the molecular weight of TCE, 1000 mg into some other terms. So finally we'll get it as 59.92 milligram per gram. So this is the final equation. Okay, just have a quick look after for it. Okay. So this is the next problem that we have. So it's related to activated sludge plant. So basically regarding the calculations of all the various aspects of ASP. Okay, so the problem says an activated sludge plant is treating municipal wastewater, and the kinetic constants are Y, Kd, K, and Ks, that are zero point 0.5, 0.05, 5, and 50 milligram BOD per liter. Okay, so the influent BOD concentration is 200 milligram per liter, and the aeration period is 6 hours, and the solid retention time is 5 days. So we have to calculate what is the effluent soluble BOD, what is the removal efficiency of BOD, what is the concentration of microorganisms in the aeration basin, what is the MLSS concentration in the MLS aeration basin, okay, what is the specific BOD utilization rate, and what is the food to microorganism ratio or the F by M ratio. Okay, and assume that VSS by TSS ratio in the mixed liquor is around 0.78. Okay, so try to solve this by yourself and then I'll give you the solution. Because it's all direct formula application. So I'll wait for some time. You try to solve it. Let's see how to solve this problem now. So A part says what is the effluent BOD concentration. So that is nothing but S is equal to Ks 1 plus Kd theta C Yk minus Kd minus 1. So very simple. Then we will put all the values. So these equations have to be memorized because it will take time for you to derive in the final exam if you want to do so. So it's better that you memorize all these formulas. Okay, so this is for the effluent BOD. Now what will be the efficiency? So that is 97.2%. Okay, so this we found out. Then what is the MLVSS or the aeration tank microorganism concentration? That is equal to, okay, so y will be equal to 0.5 into 5. I will change hours to days. So I will just change hour to days and then S naught minus S. Okay, then 1 plus Kd theta C. So Kd is 0.05 and theta c will be 5, and then theta, that is the uh, hydraulic retention time, will be 6 hours. So if we solve it, we will get 1,555 milligram VSS per liter. Okay. So direct application, this formula just have to be memorized. And so what will be the MLSS? So the ratio was given as 0.78. So MLSS will be equal to X by the ratio. So it will be 1,555 divided by 0.7578. So that is 1994 milligram per liter. Or you can say 2000 milligram per liter. Okay. And then the specific substrate utilization rate. Okay, so that is nothing but Q. It is S naught minus S by theta X. Okay, so S naught is 200 minus 5.6 into 24 hours per day. I'm just changing hours into days because the theta that is given is in 6 hours into 1,555. So you will get as 0.5 milligram of BOD per milligram of VSS per day. So this will be the utilization rate. And in the end, we have to calculate the F by M ratio. So F by M ratio is nothing but S naught by theta X. So again, okay, so only difference is here that effluent is being getting subtracted effluent concentration, and apart from it other things are same, so very minute difference will be there. So it is 0.51. So that's how you have to do. Okay, very simple. So I'll quickly show all the formulas one by one. You can make a note of it. Okay, so let's move on to the next problem. It says that in a biological treatment facility, it was found that 1 gram of microorganisms would decompose glucose at a maximum rate of 1.5 milligram per day when the concentration of glucose was high. It was also found that in the reactor at glucose concentration of 15 milligram per liter, the reaction rate is half of the maximum rate. Okay, so calculate the rate of glucose decomposition, that is ds by dt, when glucose concentration remaining is 5 milligram per liter and the microorganism concentration is 2 gram per liter. Okay, so just go through the question once again and then we will see how to solve it. Okay, so let's see the solution here. So what do you mean by specific substrate utilization rate? Okay, it's nothing but Q, which is given by 1 by x ds by dt, and it is also equal to minus ks by s, ks plus s. So this is from the Monod's equation. Okay, so my ds by dt will be, okay, so all the parameters are now given in the question. So my k value will be equal to my ks value is half saturation constant. So where the growth rate is half of maximum, substrate remaining is 5, and the amount of microorganisms is okay VSS. So everything is now known, just you have to apply. So minus ds by dt will be equal to 750 milligram glucose per liter day, or you can say minus 0. So my ds by dt will be equal to minus 0.75 gram of glucose per liter day, or minus 0.75 kg glucose per meter cube day. And this negative sign is because glucose concentration is decreasing with time. Because we are asked the specific utilization rate. So how the glucose concentration is decreasing, that's what we have to find out. Okay, just see this question again, and yeah, so that's what we have done. Okay, let's see the next problem now. So it says that determine the liquid volume before and after digestion and dewatering and the percentage reduction for 500 kg of dry basis of primary sludge with the following characteristics. Okay, so you have to find out the liquid volume before and after digestion and then dewatering. So the solid percentage is given for both the primary and the digested dewatered sludge, the volatile matter percentage, and the specific gravity of fixed and volatile solids. So try it out. Yeah, so average specific gravity of all solids in primary sludge is equal to 1 by St. So 20% by solids plus 80% of water. Okay, so from here we'll get St is equal to 1.0.88, 1.14. So this is for the primary solids. Then specific gravity of primary sludge. So it will be 1 by Sp. So 95% is water. So 5% of solids that we just calculated plus 95% water. So my volume of primary sludge will be it will be 9.9 meter cube. Okay. So that's how we have to find out the volume of primary sludge. Now what will be my volume volatile matter percentage after the digestion? Total volatile solids after digestion by total solids after digestion. So 0.8 of 500, and out of which 60% is getting destroyed. Okay, so this is the total solids. So 61.5 percentage. And then for the digested sludge you have to calculate. So all these things you have to again do it for the digested sludge. So average specific gravity. So again for the digested sludge we have to do. So 38.5% will be solids because the remaining will be water. No, this is not solids and water. This is the volatile matter. So 61.5% is the volatile matter and 38.5% is the solids, fixed solids. So this is the digested solids. Now we have to find it for the sludge. So 20% and 80%. Okay, so volume of digested sludge V will be 2.2. So that is 1.2 meter cube. So earlier was 9.9 meter cube and after digestion it has become 1.2 meter cube. So my volume reduction after digestion in percentage will be equal to 87.8 percentage. So I'm just showing you the question once again. You can take a screenshot or just make a note of it. Right? Okay, so let's see the next question. So it's a similar kind of problem, but little bit different. So just go through the problem and then we will discuss how to solve it. So it says that from the following analysis, uh, of untreated and undigested biosolids, determine the total volatile solids reduction achieved during digestion. It is assumed that the weight of fixed solids in the digested biosolids equals the weight of fixed solids in the untreated sludge. And second, the volatile solids are the only constituents of the untreated sludge lost during digestion. And the volatile solids and the fixed solids percentage are given for the untreated and the digested sludge. So just try to solve it out. Then we will see how to proceed. Okay, so let's see how to solve this problem. So for 1 kg of dry untreated sludge, fixed solids percentage will be equal to 0.32. That is nothing but 32%, right? So now let X equals the weight of volatile solids after dilution. Okay, so this is equal to, so this is the X. So this we know as 50 percentage. Okay, so from here we can get X as 0.32 kg. Okay, for 1 kg of dry untreated sludge. Now next, so the weight of digested sludge is into 2 times because it was 50%, not 5, it's into 2, so 0.64 kg. So percentage reduction in total suspended solids RTSS 1 minus 0.64 by 1 into 100, that is equal to 36%, and percentage reduction in volatile solids, so RVSS is equal to 0.68 minus 0.32, that is 0.68 into 100, so 52.9 percentage. Okay, so one more method, direct method is there, which is known as Van Cleek's method. So from here we can directly find out. So the formula is percentage in volatile solids, W of volatile solid, rate of volatile solid in feed minus weight of volatile solids in digested, divided by weight of volatile solids in feed minus weight of volatile solids in digested into weight of volatile solids in feed into 100. So this is equal to, so directly we can get the answer. Okay, so that's how you have to solve the problem. Okay, so another problem we have. So it says that in total, 500 meter cube per day of combined sludge at 2.5% solids and specific gravity of 1.01 are thickened and dewatered. The performance data of thickener and dewatering facility are given below. Determine the volume of processed sludge and side streams. Okay, you can draw the process diagram also. So for the thickener, the solids capture efficiency is 85%. Solids content of thickened sludge is 6% and specific gravity of thickened sludge is 1.015. And for dewatering facility, the solids capture efficiency is 90%. Solids content of the sludge cake is 25% and specific gravity of sludge cake is 1.02. Okay, so try it out and then we will see the solution. So let's see how to solve this problem. So dry solids in raw combined sludge is equal to 500 meter cube per day into 2.5 kg of dry solids per 100 kg of wet sludge into 1010 kg per meter cube of wet sludge. So that is 12625 kg per day. Okay, and dry solids captured by sludge thickener is around 85%. So 10730 kg per day. Now the volume of the thickened solids will be 10730 kg per day of dry solids into 100 kg of wet sludge for 6 kg of dry solids into 1 by the density of the wet sludge. So that will be equal to 176 meter cube per day. So my volume of thickener overflow will be equal to 500 minus 176. That is 324 meter cube per day. So the amount of dry solids that is captured in the sludge dewatering facility would be 90% of it. So my volume of sludge cake into 100 kg of wet sludge by 25 kg of dry solids into the density of wet sludge. So this is equal to 38 meter cube per day. So volume of side stream would be from the sludge dewatering facility one 38 meter cube per day. Okay, so if I want to draw the diagram of all the flows and everything, so suppose a raw combined flow is coming, where the volume is 500 meter cube per day. Dry solids is around 12625 kg per day. Solids is around 2.5% and the density is 1020 meter cube per kg. So it is going into a sludge thickener. Okay, it is going to a sludge thickener where 85% is being captured. Okay, so the flow that would be coming out will be 324 meter cube per day, and from here some thickened sludge will be coming out. Okay, so here the volume will be around the leftover 176 cubic meter per day. Dry solids will be around 10730 kg per day with 6% solids and a density of 1015 kg per meter cube. And it would be going into a dewatering facility with a 90% of capture. So from here the flow coming out will be 138 meter cube per day, and the rest would be sludge cake. So the volume here would be 38 meter cube leftover per day. Dry solids of 9660 kg per day, and 25% solids with a density of 1020 kg per meter cube. Okay, and the total flow from the side thickeners and everywhere will be around 462 meter cube per day. Because of this is overall diagram, right?